Hello there, and welcome to Sleep Science Space. I'm genuinely glad you've joined me tonight. In this session, we're going to drift slowly through the shifting sky above us as we explore the quiet science behind weather, the gentle breezes, towering storm clouds, soft flurries of snow, and warm sunlit moments that shape the atmosphere around us. Think of this as an invitation to rise lightly through the clouds without ever leaving the comfort of your bed or sofa. And just a small heads up, this video is meant to ease you toward rest, but every now and then, the science behind the sky can be just captivating enough to keep your mind awake for a little longer. If you do find yourself wide eyed at 2 in the morning thinking about cumulonimbus clouds or the Coriolis effect, at least you'll be a bit wiser for it. Before we get underway, I'd love to know where in the world are you watching from and what time is it there right now? Midnight sunrise or somewhere between. It's wonderful to have you here. And if you enjoy calm, curiosity driven journeys like this one, feel free to like the video and subscribe. It helps this little corner of quiet science reach others who might need a peaceful moment too. A quick reminder before we begin, although we'll be discussing temperature, air pressure, and how different kinds of weather can affect your body, everything here is for education and relaxation. It's not medical advice. If you ever have concerns about heat, cold, or weather related health issues, please reach out to a qualified medical professional. Now, if you'd like, soften your gaze or close your eyes. Let your shoulders settle and take a slow, steady breath. Tonight, we're exploring how weather works, the mechanisms behind each raindrop rainbow and distant roll of thunder. Let's begin. To understand weather, we should start with something that surrounds us constantly, but rarely gets our full attention unless it's misbehaving the air itself. We live at the bottom of a massive, invisible ocean of gases, a huge, gently moving envelope we call the atmosphere. Unlike the real ocean, no snorkel is required to breathe here, though it does sometimes fluff your hair or send papers sailing off the table. The atmosphere is the backdrop where every type of weather unfolds. Despite its importance, it's surprisingly thin, proportionally, about as delicate as the skin on an apple. If you've ever looked out the window of a plane cruising around 35,000 feet, you were already above a significant portion of it. This vast envelope of air is organized in layers, each with distinct traits almost like tiers of a layered cake, just not nearly as sweet. The lowest layer, and the one responsible for almost all the weather that affects our daily lives, is the troposphere. Clouds are born in this layer, shaped, stretched, and sculpted by constantly moving air. It's here that rain forms, winds wander, and storms gather their strength. The troposphere typically extends about 7 miles, or roughly 11 kilometers above the surface, though its height isn't fixed. Near the equator, where warm air expands upward, it reaches higher. Toward the poles, where the air is colder and more compact, it's noticeably shallower. Above this busy weather zone lies the stratosphere, home to the ozone layer, Earth's natural sun shield. The ozone layer absorbs much of the sun's ultraviolet radiation, filtering out wavelengths that would otherwise be harsh on our eyes and damaging to life. Think of it as a protective visor stretched across the upper atmosphere. Climb higher still, and you'll reach the mesosphere, a region famous for burning up meteors. When you see a shooting star streak across the sky, chances are it's disintegrating right there. Beyond that is the thermosphere, an expansive and thin layer where the auroras shimmer and satellites orbit. Temperatures here can soar to thousands of degrees Fahrenheit, but because the air is so sparse, it wouldn't feel hot. You'd barely bump into enough particles to notice. At the farthest reaches sits the exosphere, the atmospheric boundary that gradually fades into outer space. Molecules here are so widely spaced that some drift away entirely, slipping into the emptiness beyond our planet. But let's stay grounded in the troposphere, our home turf, where the real drama of weather unfolds. The air around you is a blend of gases, roughly 78% nitrogen, 21% oxygen, and the remaining percent made of argon, carbon dioxide trace gases, and varying amounts of water vapor. It's not an exotic mixture, but it's exactly the recipe life depends on. What makes this layer lively is the way air behaves. Air acts much like any other fluid. It flows, curls, churns, and responds to temperature and pressure. Warm air rises because it becomes lighter and less dense. Colder air, being heavier, sinks. This upward and downward motion is the driving engine behind many of the weather patterns we see. Sunlight heats Earth unevenly. The equator receives abundant rays, while the poles barely get a fraction. Land heats more quickly than oceans. Slopes warm differently than shaded valleys. All these differences create patches of warm and cool air across the surface, and because nature prefers balance, the atmosphere is constantly working to redistribute heat. Imagine a sunny stretch of ground. As the surface warms, the air directly above it begins to rise, and as it lifts higher into cooler surroundings, its temperature drops. Colder air can't carry as much water vapor, so any moisture in that rising pocket begins to condense into tiny droplets. And with that gentle transformation, warm air rising, cooling, and condensing, a cloud begins to take shape. As that warm column of rising air lifts away, the cooler air sitting nearby slips in to replace it. This motion air rising in one spot and sinking in another is known as convection. You can think of it as the atmosphere's quiet, steady heartbeat. The same principle draws bubbles through a simmering pot of soup or moves heat evenly through an oven. In the sky, though, the scale is immense, stretching across miles and powering everything from gentle breezes to towering storm clouds. Now let's turn to something the air is always carrying with it, even if we barely notice pressure. Air has mass, and because gravity pulls on that mass, the atmosphere presses down on us. At sea level, all that stacked air adds up to about 14 pounds of force on every square inch of your body. It's gentle, steady, and constant, like being wrapped in a soft, invisible weight at all times. We call this atmospheric pressure, and it changes with altitude and weather conditions. A high pressure system is a region where air is gently sinking toward the ground. Sinking air tends to warm and dry out, which suppresses cloud formation. The result, clear skies, stable conditions, and what many people think of as good weather. High pressure is the atmosphere in a relaxed mood. A low pressure system, on the other hand, is where air is rising, and rising air cools as it climbs, allowing moisture to condense into clouds. These systems are more dynamic, often bringing rain clouds or storms. Low pressure is the atmosphere when it's feeling energetic and expressive. Wind is simply the atmosphere trying to balance these pressure differences. Air moves from high pressure toward low pressure, flowing along invisible gradients, like water seeking the easiest path downhill. It's nature's constant attempt to tidy things up, though the result is often anything but tidy. But air doesn't move in straight lines. Because Earth is spinning rapidly at over 1,000 miles per hour along the equator, any moving air mass becomes deflected. This is the Coriolis effect, a twist introduced by the planet's rotation. In the northern hemisphere, winds bend to the right of their path. In the southern hemisphere, they veer left. It's not magic. It's just the geometry of a rotating world, shaping the motion of the air that blankets it. Add moisture to the mix. Throw in mountains and coastlines. Consider whether it's day or night, and you have a recipe for endless variation. The atmosphere is always in motion. Even on a quiet day with still branches and a pale blue sky, subtle currents glide past you. Temperature shifts, humidity ebbs and flows, and invisible boundaries of warm and cool air slide across the landscape. It's a system that behaves almost like a living organism, though it isn't alive. It's simply responsive and dynamic, governed by the same physical laws that shape oceans and stars. What's remarkable is how all of this complexity arises without any central control. There's no master switch, no conductor guiding the winds. The whole system organizes itself because of a few fundamental principles. Heat moves from warm regions to cooler ones. Pressure differences seek balance, and water continually cycles between vapor liquid and ice. The atmosphere is always reaching for equilibrium, even though it never quite gets there. And that constant striving, the endless push and pull of warm and cold, wet and dry, high and low, is what we call weather. Every breeze, every cloud, every thunderstorm is part of Earth's ongoing attempt to redistribute energy as it spins through space, wrapped in sunlight and thin, warm air. So the next time you lift your eyes and notice clouds sliding across the sky, or feel a breeze moving through your hair, you'll know those motions aren't random at all. They're pieces of a vast, interconnected system, an endless choreography shaped by sunlight, gravity rotation, and the persistent push toward balance. And all of it begins right here in the thin shell of air wrapped around our world. Now, let's turn our attention to the true engine behind nearly every weather pattern on Earth, the Sun. Although it sits about 93 million miles away, it's the dominant force shaping the atmosphere. Without the sun's energy, our planet would be a frozen, silent sphere. No rain, no winds, no storms, no whispering breezes, and definitely no need for weather forecasts that somehow manage to warn you about light showers right before you end up soaked. The sun drives weather by sending us energy in the form of electromagnetic radiation. But here's the part that often surprises people. The atmosphere doesn't absorb most of this energy directly. Instead, sunlight warms the surface, land, water, soil, forests, cities, and those surfaces then heat the air resting above them. It's similar to standing near a warm stovetop. The stove doesn't heat you with light, it heats the air, and the warm air heats you. And because the earth is tilted and curved, that heating is wonderfully uneven. The equator receives sunlight more directly and more consistently than the poles. This uneven distribution creates a persistent thermal contrast. The tropics heat rapidly, while polar regions stay much colder, and where there's contrast, the atmosphere sets to work trying to reduce it. The result is movement constant sweeping global movement. Near the equator, warm air rises, creating a zone of lower surface pressure. Air from surrounding regions flows in to replace it. The rising air cools as it ascends, spreads outward at higher altitudes, and then gradually sinks again as it moves toward cooler regions. This broad, organized motion forms what we call convection cells, enormous circulatory loops that transport energy around the planet. Because Earth is large, rotating, and covered in varied landscapes and oceans, scientists divide the main circulation into three major cells in each hemisphere. The Hadley cell closest to the equator, where strong solar heating drives tall plumes of rising air and powerful returning winds. The Ferrel cell in the mid-latitudes, a more complex mixed zone influenced by both tropical and polar air masses. The polar cell near the poles, where cold, dense air sinks and creeps outward across the surface. Together, these cells form a global conveyor system that carries heat from the equator toward the poles and returns cool air back again, keeping the entire planet's atmosphere in continuous motion. Inside these circulation patterns are the wind belts you may have heard about. Near the equator sit the trade winds, steady east to west surface winds that sailors relied on for centuries. They were so dependable that many long sea voyages, some planned, some accidental, used them to cross entire oceans. Farther out into the mid-latitudes lie the westerlies bands of winds that blow from west to east. These winds steer most of the weather systems that sweep across North America, Europe, and many other temperate regions. And closer to the poles, we find the polar easterlies, cold and dry air sliding from east to west across the icy high latitudes. All of these winds trade winds. Westerlies and polar easterlies aren't isolated phenomena. They're the surface fingerprints of the planet's larger atmospheric circulation, shaped by heating, cooling rotation, and the continuous exchange of energy between different regions. If the Earth weren't rotating, these global wind belts would simply glide in straight, predictable paths. But our planet is spinning, and that rotation adds the next layer of complexity to the story, the Coriolis effect. Because the Earth rotates at different speeds, depending on latitude fastest, at the equator slower near the poles, anything traveling long distances across the surface gets gently redirected. It's not that the air chooses to change direction, it's just following the rules of motion. When a mass of air moves north or south, it carries its original rotational speed with it. That mismatch causes the air to veer. In the northern hemisphere, moving air bends to the right. In the southern hemisphere, it curves to the left. The Coriolis effect doesn't twist water in your bathroom sink or spin a toilet bowl that's a myth. But on the scale of continents and oceans, it profoundly shapes the flow of winds. Because of it, cyclones rotate counterclockwise in the northern hemisphere and clockwise in the southern hemisphere. It's also the reason our global wind patterns form clean, organized bands rather than descending into total atmospheric chaos. If you rise even higher into the atmosphere, you encounter another major player in our weather, the jet stream. These are narrow, fast moving corridors of air that form along boundaries between large air masses. The polar jet stream is the most familiar one, a high altitude wind river flowing where cold polar air meets warmer mid latitude air. It usually snakes around the planet 6 to 9 miles above the ground and can exceed 200 miles per hour, faster in many cases than a high performance car minus the traffic jams. Jet streams form because of strong temperature contrasts. They help steer weather systems, shaping where storms develop and where heat waves or cold spells travel. When the jet stream dips far south or loops north, entire regions can experience dramatic changes in weather. And if you've ever flown eastward and noticed the trip felt quicker, you may have been riding inside that fast atmospheric current. But Earth's atmosphere isn't shaped by rotation and sunlight alone. The planet is tilted by about 23.5 degrees, and that tilt creates the seasons. As Earth orbits the Sun through the year, each hemisphere takes turns leaning toward or away from the light. When the northern hemisphere tilts toward the sun, it receives more direct sunlight and longer days, giving us summer. At the same moment, the southern hemisphere is tilted away, settling into winter. Half a year later, the balance reverses. Spring and autumn are the transition periods when both hemispheres receive similar amounts of sunlight. These seasonal shifts change how heat is distributed across the globe, which in turn affects wind patterns, the position of the jet stream, and the development of storms. And then there are the oceans covering more than 70% of the planet. They're not just large scenic reservoirs of water, they're active components of the climate system. Oceans absorb immense amounts of solar energy and release it slowly, which is why coastal areas tend to have milder temperatures than inland regions. Water warms and cools far more slowly than land. Ocean currents, like atmospheric winds, move heat around the world. The Gulf Stream, for example, carries warm water from the tropics toward Europe, warming the climate there. The Kuroshio Current plays a similar role in the Pacific. And when ocean patterns shift dramatically, as they do during El Nino or La Nina weather around the globe, responds changing rainfall in one region, causing drought in another, or altering storm behavior elsewhere. So, in just a few minutes of gentle drifting through the science, you've explored the interconnected machinery behind Earth's weather. The sun warms the planet unevenly. That uneven heating sets air in motion. The spinning Earth curves those motions into sweeping arcs. Oceans store and redistribute heat, and everything interacts in a continuous, ever shifting flow. Jet streams tug weather systems across the sky like narrow, high speed highways, and Earth's gentle tilt guarantees that no region stays in exactly the same conditions for long. The end result is a world where the atmosphere is always in motion. No 2 days are precisely alike. The breeze brushing against your face, the shape of the clouds overhead, even the rhythmic tapping of rain on your window, all of it is part of a vast planetary system powered by sunlight and sculpted by motion. It's a delicate equilibrium, one that's been running for billions of years. And remarkably, every shift in the weather, whether it's a quiet drizzle or a powerful storm, traces back to the sun's steady, distant warmth. Now, let's look at one of the most overlooked but influential parts of this system: moisture in the air. We rarely think about it unless it's making our hair unpredictable or fogging up a pair of glasses. But the invisible water vapor drifting through the atmosphere is essential. It forms clouds, drives precipitation, feeds storms, and creates many of the sky's most striking and dramatic displays. Moisture is the quiet architect of weather, and it's present even when the sky looks perfectly clear. We can start with humidity, which simply refers to the amount of water vapor in the air. Water vapor is just water in its gaseous state, and the air's ability to hold it depends heavily on temperature. Warm air can store a great deal of water vapor, while colder air can hold far less. This is why summer can feel humid and heavy, while winter air often feels crisp and dry. It isn't just perception, there truly is less moisture available in cold air. Meteorologists typically describe humidity in two ways: absolute humidity and relative humidity. Absolute humidity is the actual quantity of water vapor in a given volume of air, essentially a measurement. Relative humidity is a percentage that compares how much water vapor is in the air to how much the air could hold at that temperature. When the relative humidity reaches 100%, the air is fully saturated. It can't hold any additional moisture, so condensation begins to occur. That's when clouds, fog, and dew start forming. You've likely felt the effects of high relative humidity on a hot day. Even if the air isn't completely saturated, high humidity can make temperatures feel heavier and more exhausting. That's because sweat evaporates more slowly when the air is already packed with moisture. Evaporation is your body's cooling mechanism, and when it slows down, you feel warmer. In dry air, sweat evaporates far more easily, which can leave you cooler, but also a bit dehydrated if you're not careful. With that in mind, let's move on to clouds. They may look soft and weightless from a distance, but they're made up of staggering numbers of tiny water droplets or ice crystals if the temperature is low enough. Each droplet is so minuscule that it takes about 1 million of them to form a single raindrop. And despite their delicate appearance, an average cumulus cloud, the puffy cotton-like kind we often imagine, can weigh hundreds of thousands of pounds. In other words, it's entirely possible for a single cloud floating above you to weigh as much as a commercial jet, yet it remains suspended because the rising air underneath it supports those tiny droplets, allowing the cloud to drift peacefully overhead. But how do clouds actually begin their formation? It all starts with evaporation. Water from oceans, lakes, rivers, soil, and even vegetation absorbs heat from the sun and turns into water vapor because warm air is lighter and more buoyant than colder air. This vapor rises into the atmosphere. As it ascends, the surrounding air pressure decreases, causing the rising air to expand and cool. And cooler air simply cannot hold as much water vapor. The excess vapor condenses into tiny droplets or ice crystals, and these cling to microscopic particles such as dust, sea salt, ash, or pollen. These tiny particles are known as cloud condensation nuclei, the essential building blocks that allow water to latch on and form visible clouds. The kind of cloud that develops depends on how the air rises and how much moisture is available. When air rises slowly and steadily, it forms stratus clouds, those flat gray layers that can blanket the sky and create that familiar heavy overcast feeling. When air rises more vigorously, cumulus clouds appear. These are the classic cotton puff formations we often associate with fair weather. But if the atmosphere is unstable and loaded with moisture, those cumulus clouds can grow upward into enormous cumulonimbus structures, the towering engines of thunderstorms. There are plenty of other cloud varieties as well. High above cirrus clouds stretch out as thin icy streaks that often hint at changes in the weather. Lenticular clouds, shaped by airflow over mountains, settle into smooth lens-like forms that can easily be mistaken for unusual aircraft. Mammatus clouds hang in rounded bulges beneath storm anvils, creating dramatic textured skies. And altocumulus castellanus clouds form turret-like bumps along their tops, signaling instability in the atmosphere. Their names may sound arcane, but each one corresponds to a specific atmospheric process, making the sky a vast catalog of ongoing physics. Now, forming a cloud doesn't guarantee precipitation. For rain to fall, droplets inside a cloud must grow large enough to overcome the upward drag of the air around them. This growth typically happens through coalescence, where smaller droplets collide and merge into larger ones. When droplets reach about 2 millimeters in diameter, gravity wins out and they begin to fall as raindrops. In colder clouds, ice processes dominate instead. Ice crystals can't gather water, vapor grow into larger flakes or pellets, and eventually fall as snow if temperatures stay below freezing on the way down. And despite what cartoons have taught us, raindrops are not teardrop shaped. As they fall, air pressure flattens their bottoms, giving them a shape more similar to a tiny rounded hamburger bun. If a droplet grows too large, it may break apart into smaller ones during its descent. Not all precipitation reaches the ground in liquid form. When the entire path from cloud to surface stays below freezing snow, forms delicate ice crystals whose shapes depend on humidity and temperature. Some develop as long needles or thin plates, while the classic six-armed star patterns appear only under particular conditions. The popular claim that no two snowflakes are identical is mostly a matter of probability, with astronomical numbers of crystals forming each winter. Some are bound to be remarkably similar. If the air warms near the surface, but remains cold higher up, Snowflakes can partially melt and refreeze into sleet, or they may melt completely and then freeze instantly on contact as freezing rain. That variety is especially hazardous, coating roads, trees, and sidewalks in smooth, transparent ice. And then there is hail, which forms through a very different process. Inside powerful thunderstorms, strong updrafts lift small ice pellets repeatedly through regions of supercooled water. With each pass through the storm, the pellet gains additional layers of ice. It continues cycling upward and downward, growing in size until it becomes too heavy for the updrafts to support. Only then does it fall to the ground as a hailstone. Hailstones can vary tremendously in size, some no bigger than peas, others as large as golf balls, and in rare cases even growing to the size of grapefruits. When you hear reports of golf ball hail, it's not exaggeration. It's a real and occasionally destructive phenomenon, and definitely best appreciated from safely indoors. Of course, water doesn't always need to fall from the sky to make its presence known. Sometimes it simply settles quietly onto surfaces, as do those tiny glittering beads that appear on grass or car roofs during cool mornings. Dew forms when the ground loses heat overnight, cooling the air just enough for water vapor to condense. If temperatures drop below freezing, that moisture crystallizes into frost, painting leaves, rooftops, and windows with delicate ice patterns. All of these transformations, evaporation, condensation, precipitation, are steps in the water cycle, Earth's long running system for endlessly recycling its water. Liquid water evaporates from oceans and lakes, travels upward, forms clouds, falls as rain or snow, and eventually returns to streams and seas to begin again. This cycle has been operating for billions of years and underpins nearly every ecosystem on the planet. Clouds and rain don't require still air either. In fact, many of the most noticeable weather changes occur along fronts, the boundaries where contrasting air masses meet. When warm, humid air encounters a cooler, denser air mass, the warm air is forced upward. As it rises, it cools, moisture condenses, and clouds thicken often, leading to rain or storms. It's why a shifting front can dramatically change the sky in minutes. So the next time you look up and see a cloud drifting by, know it's not just a patch of fluff. It's a visible sign of countless invisible processes working together. Every drop of dew, every wisp of fog, every passing shower reflects a precise balance of temperature, motion, and moisture. And virtually all of it begins with water vapor, quiet, unseen, and absolutely essential. When the atmosphere becomes especially energetic, it sometimes produces thunderstorms, nature's version of a grand atmospheric performance. They flash boom and pour occasionally, hurling chunks of ice with surprising enthusiasm. Yet even these dramatic displays arise from familiar ingredients, warm air moisture, and a bit of electrical charge. At the core of every thunderstorm is rising warm, moist air. This upward surge, called an updraft, often begins on hot afternoons when the sun has been warming the surface for hours. The air near the ground becomes hotter and lighter than the air above it, so it begins to rise. As it climbs, the pressure drops and the air expands and cools. Eventually, if it cools to its dew point, the water vapor it contains condenses into tiny cloud droplets. Condensation releases latent heat, which warms the rising air slightly and helps it continue upward, like giving a small lift to a balloon already on its way. A small cumulus cloud begins to grow. With enough moisture and instability, that cloud can rapidly develop into a towering cumulonimbus, a massive vertical structure that can reach heights of 50,000 feet or more, far above the level of typical airplane travel. Inside this growing cloud, opposing forces are at work. Strong updrafts continue lifting warm, moist air higher, while cooled air and precipitation start descending in a downdraft. The storm is beginning to organize itself, setting the stage for lightning thunder and all the drama that follows. The rising and sinking of air inside the cloud is the heartbeat of a thunderstorm. These currents, warm air rushing upward and cooler air pouring downward, are what power the storm's entire engine. Once those updrafts and downdrafts become strong and organized, the storm is officially alive. Thunderstorms move through three main stages: the cumulus stage, the mature stage, and finally, the dissipating stage. In the cumulus stage, warm, buoyant air rises steadily and builds the first cloud. It's a quiet, gentle phase, like slowly inflating a balloon, all potential and no drama yet. Then comes the mature stage, where the storm reaches its full strength. The cloud towers upward, raindrops begin to form and tumble downward, lightning flickers through the sky, and thunder begins to speak. This is the moment when rising air and falling air exist side by side in a swirling, turbulent dance. Eventually, the storm enters the dissipating stage. Falling rain cools the air beneath the cloud, cutting off the warm fuel the storm depends on. With no more rising heat to drive it, the thunderstorm gradually weakens, shrinks, and slips away. But before it fades, a thunderstorm puts on its most dramatic performance: lightning. Lightning is nature's way of redistributing electrical charges, though it certainly chooses a theatrical method. Inside the churning cloud, tiny ice crystals and water droplets collide over and over, collecting electrical charge as they do. Lighter ice particles carry positive charge and are swept upward, while heavier hail and droplets gather negative charge and sink toward the cloud's base. This separation builds a tremendous electrical imbalance, millions of volts between different parts of the cloud, between cloud and ground, or even between neighboring clouds. Eventually, the air can no longer insulate those charges, and a sudden discharge occurs. The process begins with a stepped leader, a faint branching path of charged particles descending quietly from the cloud. When it comes close to the ground, the electric field strengthens enough to send a streamer upward to meet it. When they finally connect, an enormous current rushes along the channel, creating the brilliant flash we recognize as lightning. Inside that channel, the air is heated to nearly 50,000 degrees Celsius in just millionths of a second, hotter than the surface of the sun. That extreme heat forces the air to expand explosively, producing a shock wave that we hear as thunder. Because light travels so much faster than sound, We always see the flash before we hear the rumble. If you want to estimate how far away a strike is, count the seconds between lightning and thunder. Divide that number by 5 to get the distance in miles. 10 seconds, roughly 2 miles away. Lightning also comes in many varieties. Cloud to ground lightning is the most striking and hazardous type, especially if you happen to be standing in an open field holding something metal and ill advised. Intra-cloud lightning zigzags within a single cloud, while cloud to cloud lightning leaps dramatically between two separate storm towers. And then there are the rare, almost mystical forms, ball lightning, glowing spheres that remain mysterious even today, and high altitude electrical events known as sprites and blue jets. Sprites, in particular, appear far above thunderstorms as delicate reddish shapes resembling jellyfish. Pilots once reported them only to be doubted, but now we know they're real stunning and part of the atmosphere's hidden light show. Lightning may be beautiful to watch, but it's also astonishingly powerful. A single bolt can unleash over 1 billion joules of energy, enough to power a small town for a heartbeat. That same energy can spark wildfires, split trees, damage rooftops, and tragically, it can be dangerous to people. It's why safety experts gently remind us when thunder roars, go indoors. Not the most poetic rhyme, but undeniably wise. Thunderstorms often bring other dramatic gifts from the sky, like hail. As we touched on earlier, hailstones are born high inside the storm's powerful updrafts. Water droplets are swept upward, freeze, fall back down, and then get tossed upward again each cycle, adding a fresh icy layer. It's like a miniature snowball being dipped into freezing bunners over and over. Eventually, the hailstone becomes too heavy for the updraft to hold aloft, and it plummets toward the ground. Depending on the strength of the storm hail, can range from pea-sized pellets to astonishing softball-sized chunks of ice. And then, of course, there's wind. Thunderstorms create strong and sometimes sudden bursts of wind as their downdrafts drag cool air downward. When that air hits the ground, it spreads outward in all directions, forming what's known as a downburst. These winds can be surprisingly destructive and are sometimes mistaken for tornadoes, even though they behave quite differently. Speaking of tornadoes, yes, some thunderstorms are capable of producing them, but only a special class of storms called supercells have the right structure. A supercell is built around a rotating updraft called a mesocyclone. This spin begins with wind shear changes in wind speed or direction with height, which sets up a gentle horizontal roll in the atmosphere. If a strong updraft tilts this roll upright, it can begin rotating vertically inside the storm. Once that vertical rotation tightens and intensifies, a funnel cloud may form beneath the storm's base. If that funnel touches the ground, it becomes a tornado. These events require a rare combination of ingredients, which is why most storms never produce tornadoes. But when they do occur, they are among the most intense natural forces on Earth. Most thunderstorms, however, lead far simpler lives. Short, energetic bursts of rain, lightning, and wind. They can form in clusters, known as multicell storms, or along the boundary of a cold front where advancing cool air lifts warm, moist air rapidly upward. One especially interesting feature connected to thunderstorms is the gust front. This is the leading edge of cold air spreading out from the storm's downdraft. When it moves outward, it pushes the warm air ahead of it upward, sometimes creating new storm cells. In this way, a single thunderstorm can spark a chain of new ones, a meteorological relay where each storm tags the next. Despite their drama, thunderstorms are extraordinarily common. At any moment, roughly 2,000 thunderstorms are active somewhere on Earth. While you're tucked comfortably in bed, listening to this gentle narration, somewhere else, the sky is brightening with electric flashes and grumbling with deep rolling thunder. Each of these storms is a fleeting release of the atmosphere's stored energy, a brief moment of imbalance, corrected by towering clouds, rising heat, and electric fire. And every flash, every rumble, is just the sky letting out a long charged exhale. These powerful tempests are the showstoppers of Earth's weather, huge swirling engines of energy capable of reshaping landscapes, snapping trees, and redrawing coastlines. They're loud, they're dramatic, and at times they're unsettling. But beneath all that ferocity, they obey the very same atmospheric rules as any gentle breeze air trying to balance itself. Moisture rising and falling, pressure, shifting motion, feeding motion, only everything is amplified as if someone turned the dial all the way up. Let's start with tornadoes. A tornado is a rotating column of air that stretches from the underside of a thunderstorm down to the ground. Compared to hurricanes, they're brief, often surviving only minutes, but in those minutes, they can unleash the strongest surface winds ever recorded on our planet. The most violent tornadoes have been estimated at over 300 miles per hour, outpacing a Formula One race car, and with much less concern for anything in their way. We still don't fully understand every step that leads to a tornado, but meteorologists have identified several essential ingredients. First, you need a very powerful thunderstorm, most often a supercell, the same class of storm we explored earlier. Supercells are unique because they host a rotating updraft known as a mesocyclone. This spin begins with wind shear, meaning winds at different heights, blow in different directions or at different speeds. Imagine a warm southeasterly wind near the surface while higher up, a faster westerly wind races overhead. That mismatch sets up a horizontal rolling motion in the atmosphere. When a strong thunderstorm builds above this zone of hidden rotation, the storm's updraft can tilt that rolling air upright. Suddenly, you have a vertical column of slowly spinning air rising through the heart of the storm. But this is only the beginning. Most mesocyclones will never spawn a tornado. For a funnel to form that rotation has to tighten and stretch downward toward the ground, a process influenced by tiny variations in moisture, temperature, and pressure. Some storms tease meteorologists for hours, showing every sign of producing a tornado and then never quite doing it. Others spin one up with startling speed. Once a tornado forms, it can move across the landscape at anything from a slow walking pace to over 70 miles per hour. Fortunately, most tornadoes are on the weaker side, classified as EF0 or EF1 on the enhanced Fujita scale. These might snap branches, peel shingles, or knock over smaller structures. But every so often, a truly extreme tornado emerges, an EF4 or EF5. These giants can reduce sturdy homes to rubble, uproot trees, and scatter vehicles as if they were toys. The enhanced Fujita scale ranks tornadoes from 0 to 5 based on the damage they leave behind. An EF0 might scatter debris and bend signs. An EF5 can scrape buildings from their foundations and leave behind a landscape that barely resembles what was there minutes before. Tornadoes occur in many parts of the world, but the United States sees more of them than any other country. A region often called Tornado Alley, stretching from Texas through Oklahoma, Kansas, Nebraska, and into South Dakota, is particularly well known for frequent powerful storms. It's an area where warm, humid air from the Gulf meets dry air from the southwest and colder air from Canada, creating an energetic blend that storms love to feed on. The geography of Tornado Alley is tailor-made for twisters. Warm, moisture-rich air flows north from the Gulf of Mexico. Crisp, dry air spills down from the Rockies and Canada, and the two collide beneath a vast open sky. It's a natural mixing bowl for atmospheric instability. But tornadoes aren't exclusive to this region. They've been documented on every continent except Antarctica. Waterspouts, essentially tornadoes, that spin over water frequently appear near Florida and in parts of the Mediterranean. Even the United Kingdom, not exactly famous for severe weather, sees a handful of tornadoes each year, though they tend to be milder and far better behaved than their North American cousins. Now let's step away from these short-lived whirlwinds and turn our attention to their larger, slower, and far more enduring relative, the hurricane. Hurricanes, called cyclones in the Indian Ocean and typhoons in the Western Pacific, are enormous rotating storm systems that grow over warm ocean waters. They can stretch hundreds of miles across and persist for days or even weeks. If tornadoes are explosive, dancers, hurricanes are vast atmospheric engines churning relentlessly across the sea. To build one of these giants, several ingredients have to align. First, the ocean surface must be warm, generally, at least 79 degrees, and that warmth has to extend well below the surface, about 150 feet or so. This deep reservoir of heat is the storm's energy source. Second, you need a pre-existing disturbance, such as a cluster of thunderstorms. And third, the atmosphere must have low vertical wind shear. If winds change too much with height, they tear newborn storms apart before they can organize. When conditions are favorable, warm seawater evaporates, loading the air with moisture. That moist air rises, cools, and condenses into towering clouds, releasing latent heat, the hidden energy that fuels both thunderstorms and tropical cyclones. This newly warmed air rises even faster, creating a cycle of upward motion. As the air spirals inward, thanks once again to the Coriolis effect, a central low-pressure zone develops. At this stage, the system becomes a tropical depression. If it strengthens, further organizing its circulation and drawing in more moisture, it's upgraded to a tropical storm. and once its sustained winds reach 74 miles per hour, it officially becomes a hurricane. A mature hurricane has a surprisingly structured anatomy. At the heart of the storm is the eye, a calm region of sinking air where winds are gentle and the sky may appear startlingly clear. Encircling the eye is the eye wall, a ring of violent thunderstorms containing the storm's fiercest winds and heaviest rainfall. This is the region responsible for the most severe destruction. Extending outward are rain bands, spiraling arcs of showers, and storms that can stretch hundreds of miles across the ocean. Hurricanes are classified using the Saffir-Simpson scale, which ranks storms from Category 1 to Category 5 based on sustained wind speeds. A Category 1 hurricane with winds between 74 and 95 mph can damage roofs, topple trees, and knock out power. A Category 5 hurricane with winds exceeding 157 mph can devastate communities, flatten structures, and render entire regions uninhabitable for extended periods. And wind is only part of the danger. Hurricanes also push the ocean inland through storm surge or rise in sea level caused by powerful winds piling water onto the coast. Storm surge is often the deadliest part of a hurricane, especially in low-lying coastal zones. Combined with torrential rain, it can produce massive flooding that sweeps away homes, roads, and everything in its path. Rainfall itself is another hazard. Some hurricanes unload 2 feet or more of rain within a matter of days, causing flash floods and landslides far from the shoreline. Slow-moving storms can drench regions for days, spreading damage well beyond the direct path of the eye wall. Despite their destructive potential, hurricanes play an important role in Earth's climate. They help shuffle excess heat away from the tropics, sending energy toward the poles. In their dramatic, often violent way, they participate in the atmosphere's continual effort to even out temperature imbalances across the planet. And unlike tornadoes, hurricanes are far easier to monitor and forecast thanks to satellites' radar and powerful computer models, giving communities precious time to prepare. Meteorologists can usually give several days of advance notice before a hurricane arrives in enough time for coastal communities to prepare secure their homes or evacuate if needed. Even with that warning, these storms remain enormously challenging to handle once they make landfall. Their scale, momentum, and energy make them forces that can only be endured, not redirected. And then, almost abruptly, they begin to unravel. When a hurricane drifts over cooler waters or moves inland away from its warm oceanic fuel, its engine starves. The storm weakens its winds, slacken, and its fury dissolves into lingering rain and scattered gusts. What follows may be days or weeks of cleanup, but meteorologically speaking, the storm has completed its life cycle from sun-warmed sea to a spinning atmospheric titan to a fading spiral of clouds. For all their destructive capability, tornadoes and hurricanes are not anomalies. They're the natural consequences of the same atmospheric rules that shape every breeze and raindrop heat, redistributing itself pressure, attempting to balance out the never-ending motion of air and moisture. When you watch a thunderstorm crackle across the horizon or see satellite images of clouds coiling above an ocean, you're witnessing Earth's most powerful expressions of that restless pursuit of equilibrium. They can be frightening, yes, but they're also astonishing, vast, dynamic demonstrations of a sky that is very much alive. Wind is one of the most elegant manifestations of that motion. It's the unseen sculptor of the landscape, tugging at your clothes, rustling, treetops sweeping dust across open fields, and on occasion, turning your umbrella inside out in an act of atmospheric mischief. Sometimes gentle, sometimes ferocious wind is simply air refusing to stay put. At its core, wind exists because of pressure differences. When one region has higher air pressure and another has lower pressure, air naturally moves from the high pressure area toward the low pressure one. The bigger the difference, the stronger the wind. It's the atmosphere's attempt to straighten out its own imbalance, though the process isn't always as tidy as the intention. Imagine those pressure differences as hills and valleys. Air flows downhill from high to low, just as water would, except air's journey is curved, not straight. The rotation of the Earth introduces a twist thanks to the Coriolis effect, nudging moving air to the right in the northern hemisphere and to the left in the southern hemisphere. This subtle bend shapes everything from gentle breezes to massive global wind belts. Let's begin at the planetary scale. Near the equator, where sunlight pours down most directly, the surface heats intensely. Warm air rises here, creating a belt of low pressure. High above the surface, that rising air fans out toward the poles, eventually cooling and sinking around 30 degrees latitude in each hemisphere. These sinking zones create bands of high pressure. Air then flows back toward the equator along the surface, forming the reliable east to west trade winds. Early sailors depended on these winds, using them to cross oceans, sometimes reaching their intended destinations, sometimes discovering entirely new ones. The world's great voyages were powered as much by these global winds as by human ambition. Between 30 degrees and 60 degrees latitude, the pattern reverses. Here the westerlies dominate, blowing from west to east and steering most of the weather that sweeps across North America and Europe. Closer to the poles, cold, dense air spills outward, forming the polar easterlies, which carry frigid air toward the mid-latitudes. Together, these circulation zones create Earth's major wind belts and help establish the jet streams that ribbon through the upper atmosphere. But wind isn't only a global force, it's also profoundly local. Some of the most interesting winds are shaped by mountains, valleys, and coastlines on a much smaller scale. Consider sea breezes. On a bright, warm day, land heats up faster than the ocean. The air above the land rises, forming an area of lower pressure. Cooler, denser air from over the water flows inland to replace it, creating a refreshing breeze off the sea. After sunset, the pattern flips. The land cools quickly, while the ocean stays warm, and now air flows from the land toward the water. This graceful daily exchange is one of the simplest, most soothing wind patterns nature offers, a quiet, reliable breath of the coastal atmosphere. In mountainous regions, wind becomes even more dramatic, almost theatrical, in the way it flows and reverses through valleys. During the day, sunlight warms the slopes, heating the air that hugs the mountainside. That warm air rises, pulling cooler valley air upward behind it in what meteorologists call an anabatic wind. After sunset, the process flips. Mountain air cools rapidly, becomes dense, and drains downslope into the valley as a katabatic wind. These gentle daily shifts can create surprising changes in temperature, and for anyone living in a mountain town, they're simply part of the rhythm of everyday life. Some katabatic winds are famous in their own right. The Mistral of southern France is a cold, dry wind that sweeps down the Rhone Valley and rushes toward the Mediterranean. It can be fierce, often topping 50 miles per hour, and it has shaped the region's climate culture and even its architecture. Many homes are built with sheltered sides or small windows facing away from its path. On the other side of the world, California experiences the Santa Ana winds, hot and extremely dry gusts that blow from the desert toward the coast during certain seasons. These winds can rapidly dry out vegetation and fan wildfires, giving their arrival a mix of beauty tension and unease. Then there are the Chinook winds, sometimes called snow eaters. These powerful warm winds descend along the eastern slopes of the Rocky Mountains. As air falls down the mountain, it compresses and heats rapidly, sometimes raising temperatures by 40 degrees in under an hour. One moment you're stepping into a frosty winter morning, and the next you're loosening your scarf in what feels like an abrupt spring afternoon. It's as if nature briefly turned on a colossal hairdryer. Wind isn't always grand or sweeping, it can also be sudden and sneaky. A microburst, for example, is a compact but extremely intense downdraft that forms inside some thunderstorms. A column of air plunges downward, hits the ground, and spreads outward with explosive force. These bursts can flatten trees, damage structures, and pose severe hazards to aircraft during takeoff and landing. And while they can mimic the chaos of tornado damage, their structure is entirely different. On the gentler end of the spectrum, we get dust devils, tiny whirlwinds that raise from hot, dry surfaces when sunlight heats patches of ground unevenly. They spin upward like miniature tornadoes, lifting dust and leaves in playful spirals. They're usually harmless, whimsical little columns of air commonly seen in deserts, fields, or even parking lots on hot afternoons. At larger scales, we encounter gales and cyclones, wind systems tied to strong, low pressure areas. A gale with sustained winds over 39 miles per hour can bend trees and make walking difficult. Cyclones, whether they're called hurricanes, typhoons, or simply tropical cyclones, can unleash hurricane force winds, pounding rain, and destructive storm surges. These systems are vast and powerful, driven by the same atmospheric forces that move the smallest breeze. But wind isn't always dramatic. Some winds are quiet, steady background features of our atmosphere, like the jet streams high above Earth's surface. These narrow, fast moving ribbons of air flow at 100 to 200 miles per hour, meandering like rivers in the upper atmosphere. Jet streams form where cold and warm air masses meet, and they shift with the seasons. Their wandering paths influence storm development, guide weather systems, and even help determine the length of your flight. When a jet stream dips unusually far south or stalls in place, it can lock a region into days of heat, cold rain, or drought. Despite being invisible, wind shapes the world in profound ways. It transports moisture across continents, spreads seeds and pollen sculpts, desert dunes and snowy drifts, and grinds mountains into grains of sand over long stretches of time. It pushes sailboats across oceans and spins the blades of wind turbines that generate clean electricity. It is both a gentle whisper and a tremendous force. Throughout human history, we've relied on the wind as both guide and power source. Sailors once used it to explore the world. Farmers watched it for signs of shifting weather. Today, we capture its energy with vast wind farms turning the atmosphere's restless motion into renewable power. Wind also helps regulate temperature. A breeze can cool you by carrying away heat and evaporating moisture from your skin. On cold days, that same process makes temperatures feel colder than they actually are, a concept known as wind chill. The thermometer might read one thing, but the wind can convince you otherwise. And though wind seems chaotic, every gust follows the physics of pressure, gradients, gravity, and the turning earth. Whether it's the soft rustle of leaves or the distant howl of a storm wind is a language the atmosphere speaks constantly. So the next time you hear branches sway outside your window or feel a cool gust brush your cheek, pause for just a moment. That invisible movement is one of the clearest signs that the sky around you is alive, always shifting, always breathing, and always filled with quiet, persistent power. When winter settles in, it rarely arrives politely. It transforms everything it touches. Trees stand bare and motionless ponds glaze over like sheets of glass, and the air sharpens into something that nips at your nose and fingertips. Snow blankets rooftops muffles sound and turns familiar landscapes into quiet white scenes. But beneath this serene surface lies a complex world of cold weather physics. Snow, ice, sleet, and freezing rain aren't just poetic variations of winter, they are signatures of the atmosphere, behaving at its chilliest and most dramatic. Let's begin with snow, the most iconic symbol of the season. A snowflake begins its life high in the atmosphere as a tiny particle of dust or pollen, water vapor, condenses onto this microscopic speck and freezes, forming an initial ice crystal. As that crystal floats through the cloud, it encounters different layers of temperature and humidity, causing more vapor to freeze onto it in intricate patterns. The conditions shift constantly as the flake drifts downward, which is why the chances of finding two perfectly identical snowflakes are astonishingly small. Most snowflakes adopt the familiar six-sided shape, a hexagon, because water molecules naturally bond at specific angles that repeat in symmetrical patterns. Some flakes grow into thin plates, others into needles, hollow columns, or ornate star shapes. Under a microscope, they reveal astonishing geometric beauty, each one a tiny frozen sculpture shaped entirely by temperature, moisture, and motion. Snow may seem light and delicate, but it adds up quickly. A single cubic foot of fresh powder can weigh anywhere from 5 to 15 pounds, depending on its moisture content. When millions of flakes pile up, the weight becomes significant, bending tree limbs, burdening rooftops, and transforming a gentle snowfall into something heavy and structural. Wet snow, the kind that sticks easily to boots and branches, is denser and heavier than the dry, powdery snow beloved by skiers. Not all frozen precipitation forms so elegantly. Sleet begins its journey as snow falling from a cold upper atmosphere. As the flakes drop, they pass through a layer of warm air and partially melt into droplets only to refreeze into tiny ice pellets when they encounter colder air again near the surface. These little pellets bounce when they land and create a crunchy, glassy layer that's slippery but usually manageable. Freezing rain, however, is an entirely different story. It also starts as snow high above, but the snow melts completely into rain as it falls through a thicker, warm layer. Then, just before reaching the ground, it moves into a very shallow layer of freezing air. The raindrops become supercooled, meaning they remain liquid even though the air is below freezing. The instant those droplets touch a cold surface, a branch, a car, a sidewalk, they freeze solid, creating a smooth glaze of ice. This type of ice is breathtaking and dangerous at the same time. Trees and fences sparkle like crystal sculptures, but roads become treacherous and sidewalks transform into hidden traps. Freezing rain is notorious for causing power outages because the accumulating ice adds enormous weight to lines and branches, often snapping them. Then there's frost, the delicate lacework of ice that forms on cold surfaces during calm, clear nights. Frost occurs when surface temperatures fall below both the dew point and the freezing point. Water vapor in the air deposits directly as ice crystals without becoming liquid first. The result is a fine white coating that forms intricate feathery shapes on grass windows and windshields. A more dramatic cousin of frost is hoarfrost, which forms under very specific conditions: clear skies, light winds, and air saturated with moisture. Ice crystals grow outward in elaborate needle-like structures, covering landscapes with sparkling patterns that look almost otherworldly. Unlike snow, frost doesn't fall from the sky. It grows quietly in place, like a tiny frozen forest, forming molecule by molecule. In extremely cold regions, winter may even produce ice fog. This occurs when supercooled water droplets in the air freeze into tiny ice crystals suspended near the ground. It's common in places like Alaska and northern Canada, where temperatures plunge far below zero. Ice fog gives the air a silvery, shimmering quality and reduces visibility in the same way regular fog does, only with a sparkling, frozen edge. Of course, winter isn't shaped by temperature alone. Wind plays a major role in how cold we actually feel. On calm days, your skin warms a thin layer of air around your body, creating a small insulating buffer. But wind strips that warm layer away, forcing your body to work harder to maintain its temperature. This is the concept of wind chill, a measure of how quickly heat is pulled from your skin. Wind chill doesn't lower the actual air temperature, but it changes your body's experience of it dramatically. A cold day with strong wind can feel bitterly colder than a still day with the same reading on the thermometer. It's the atmosphere's way of reminding us that winter weather is not just about numbers, it's about the interplay of temperature, moisture, and motion swirling all around us. Wind strips away that thin layer of warm air surrounding your skin, forcing your body to work harder to maintain its temperature. The faster the wind blows, the faster heat is lost, and the colder the air feels. For example, if the temperature is 20 degrees, but the wind is blowing at 15 miles per hour, it can feel closer to 5 degrees. Wind chill doesn't change the actual air temperature, but it does change how rapidly your body loses heat, which affects how quickly frostbite or hypothermia can occur. It's a reminder that wind isn't only a gentle summer breeze, it can also deliver a sharp winter bite. Then we have blizzards, the heavyweights of winter storms. A blizzard isn't defined by how much snow is falling. Instead, it's defined by wind and visibility. By meteorological standards, a blizzard requires sustained winds or frequent gusts of at least 35 miles per hour, combined with visibility of a quarter mile or less lasting for at least 3 hours. You can even have a blizzard without new snowfall if loose snow is being whipped around by strong winds. Blizzards can bring cities to a halt, strand travelers, and create whiteout conditions, where even familiar surroundings disappear into a blur of swirling snow. Yet, despite their intensity, blizzards begin with the same basic ingredients as many other storms: moisture, cold air, and atmospheric instability. Snow squalls, on the other hand, are the quick, unpredictable bursts of winter weather. These brief but intense episodes of snow and wind can appear suddenly, reducing visibility in seconds. They often last less than an hour, but can produce abrupt temperature drops and dangerous driving conditions. If you've ever watched clear skies collapse into a sudden wall of white, you've likely encountered a snow squall. For all its challenges, winter weather plays a vital role in Earth's systems. Mountain snowpack provides crucial fresh water when it melts in spring and summer. Ice helps regulate the planet's temperature by reflecting sunlight back into space. Even a simple layer of snow or frost can insulate soil and protect plant roots from extreme cold. So the next time you see your breath in the air or catch a snowflake on your glove, remember that you're witnessing one of the atmosphere's most intricate performances. Each icy detail, from a frost coated branch to a snow covered field, is shaped by precise, elegant physics. And behind the silence of falling snow lies a story of temperature, motion, moisture, and time, written in frozen crystals and carried gently by the wind. Some weather arrives without drama: no thunder, no lightning, no swirling snowfall, just a gradual thickening of the air, a soft gray veil that blurs the horizon and quiets the morning. This is fog, the most subtle of the atmosphere's creations. It doesn't roar or flash. It drifts, curls, and transforms the familiar into something muted and mysterious. And although fog seems simple, it's a phenomenon filled with delicate science. At its essence, fog is simply a cloud touching the ground. It forms when water vapor condenses into tiny droplets suspended near the surface. These droplets are so small they don't fall as rain. They float, scattering light in every direction and reducing visibility. The world feels closer and quieter, and ordinary landscapes take on a dreamlike quality. There are several types of fog, each shaped by temperature, humidity, geography, and time of day. One of the most common is radiation fog. It forms on calm, clear nights when the ground cools rapidly. As the ground loses heat, it chills the layer of air just above it. If that air is moist enough and the temperature drops to the dew point, the moment air becomes saturated, condensation begins. Tiny droplets appear and fog settles in. This type of fog often develops in valleys or low-lying areas where dense, cool air gathers. It typically appears in the hours just before sunrise and lifts gradually as sunlight warms the surface. Radiation fog is fragile. A light breeze can disperse it, and morning sun can dissolve it slowly, as though someone were drawing a curtain back from the landscape. Another form is advection fog, which doesn't depend on nighttime cooling, but instead forms when moist air moves across a cooler surface, such as warm sea air drifting over a cold coastline. The cold surface cools the moist air above it, and once that air reaches its dew point, fog begins to form. Advection fog can spread over wide regions and may linger for many hours if the cooling continues. It's especially common along coastlines where warm marine air meets cooler land or ocean surfaces. This is the classic blanket of fog, often described in maritime stories and shown in lighthouse scenes, dense, steady, and capable of stretching for miles. Upslope fog is another variety found in hilly or mountainous landscapes. This type forms when moist air is pushed uphill by wind. As it rises, the air encounters lower atmospheric pressure and cools. If it cools enough to reach its dew point, fog develops along the slope. Unlike radiation fog, which is tied closely to nighttime cooling upslope, fog can form at any hour and may persist until wind patterns change. A more unusual form is evaporation fog, sometimes called steam fog. This develops when cold air moves over warmer water. You can often see it hovering above lakes, rivers, marshes, or even outdoor hot tubs on chilly mornings. The warm water adds moisture to the cool air just above it. When that sudden burst of moisture mixes with the cold air, condensation forms immediately, producing delicate wisps of fog that rise and curl like steam. It's brief, visually striking, and often vanishes as the surrounding air warms. One of the most dramatic types is freezing fog. This occurs when the air temperature is below freezing, yet the fog droplets remain in a liquid supercooled state. These microscopic droplets can stay liquid well below 32 degrees Celsius. When they touch a surface, tree branches, guardrails, car mirrors, they freeze instantly. This creates a coating of rime ice, a rough, opaque white layer that gives the environment a frosted, sculpted appearance. Unlike ordinary frost, which forms from vapor depositing directly as ice rime develops when liquid droplets freeze upon contact. It can build up rapidly and create hazards for roads equipment and aircraft, but it also transforms landscapes into striking displays shaped by wind and cold. Mist is closely related to fog, but by definition, it is less dense. The difference is visibility. If you can see more than 1 kilometer, around 6/10 of a mile, it's classified as mist. If visibility falls below that threshold, it becomes fog. Mist feels lighter, a softer version of the same phenomenon formed by the same tiny droplets under similar atmospheric conditions. Haze, however, is a different story. Though it can resemble fog from a distance, haze is caused by dry particles in the air rather than water droplets. These particles often come from dust smoke or pollution and scatter light differently, giving the sky a muted, washed out look. Haze doesn't feel damp or cling to surfaces, but it can still reduce visibility and affect air quality, making breathing more difficult for sensitive individuals. Fog also influences sound in interesting ways. When fog is dense, sound waves scatter in unpredictable patterns. They may be muffled, distorted, or seem to shift positions. A distant horn might sound faint one moment and surprisingly close the next. This effect contributes to the sense of disorientation fog can create. It doesn't only change what you see, it subtly alters what you hear. Light behaves differently too. Headlights gaining into thick fog illuminate the suspended droplets, scattering light back toward the source and producing glare. This is why driving in fog can be challenging. High beams worsen the problem by reflecting off the droplets directly in front of the vehicle. Fog lights mounted lower and aimed beneath the densest part of the fog help cut through that reflective layer just enough to reveal the road ahead. Fog also holds a quiet place in culture and emotion. It appears in stories, films, poems, and even bedtime tales because it changes how we perceive the world. Fog can feel calm or unsettling, comforting or unfamiliar. It creates a mood simply by existing, encouraging us to pause and pay attention. It slows the world down. Yet beneath all of that atmosphere and symbolism is straightforward physics. Dew points, condensation, cooling surfaces, and the movement of air. Fog may seem like the gentlest form of weather, but it is shaped by very active processes. The next time you find your surroundings wrapped in fog, take a moment to notice it. Feel the moisture on your skin. Watch how the air thickens and shifts, and remember that you are standing inside a cloud, one built at ground level instead of high above. It is weather at its closest drifting around you in a thin layer between air and water, between clarity and obscured distance. Sometimes weather doesn't arrive with intensity. There is no lightning or rolling thunder, no sudden snowfall or dramatic gusts of wind. Instead, it builds gradually, raising the temperature degree by degree until the air feels heavy, movement slows, and even a breeze brings little relief. This is the realm of heat waves and droughts periods when heat accumulates. Moisture disappears and the landscape begins to show the strain. A heat wave is more than just a hot afternoon. It is an extended period of temperatures far above the seasonal average, often lasting several days or more. The exact threshold depends on the region. What qualifies as extreme heat in a cool coastal city might be perfectly normal in a desert climate. But generally, a heat wave lasts at least 3 days with persistent, unusually high temperatures. Some continue for a week or two. A few last even longer when the atmosphere becomes locked into a stable pattern. The primary driver behind most heat waves is a strong high pressure system. On weather maps, this appears as a ridge. High pressure causes air to sink, and sinking air warms as it compresses. It also suppresses cloud formation. With fewer clouds, more sunlight reaches the surface, heating it further. Because the air is not rising, rain is unlikely. The landscape absorbs day after day of solar energy, and the heat accumulates. Local geography can intensify this effect. Cities with their asphalt concrete buildings and vehicles create what is known as the urban heat island. Urban surfaces absorb heat efficiently during the day and release it slowly at night, keeping temperatures elevated long after sunset. This is why summer nights in cities can feel unusually warm, while nearby rural areas cool down more quickly. Natural surfaces like soil vegetation and open fields radiate heat more effectively than paved streets and rooftops. Humidity also influences how we experience heat. When the air is humid, sweat evaporates more slowly. Because evaporation is one of the body's main cooling processes, reduced evaporation makes the heat feel more intense than the thermometer indicates. This is the purpose of the heat index, a measure of how hot it feels once humidity is included. For example, if the temperature is 95 degrees with relative humidity at 55%, the heat index may climb to around 110 degrees. The air itself hasn't reached 110, but your body experiences conditions similar to that temperature because it cannot cool efficiently. That's the kind of heat that softens asphalt and makes you rethink wearing jeans in midsummer. But beyond discomfort, prolonged heat can become a serious health risk. Heat exhaustion and heat stroke are genuine medical emergencies, especially for older adults, young children, and individuals with underlying health conditions. Warning signs can include dizziness, rapid heartbeat, nausea, headache, or confusion. During major heat waves, emergency services often see a sharp rise in calls and hospital visits. This is why access to shade hydration cooling centers and simple tools like fans or air conditioning can play a critical role in keeping people safe. Now let's turn to droughts, the quieter, slower moving counterpart to heat waves. While heat waves make themselves known immediately, droughts unfold gradually. A drought begins when rainfall falls below normal levels for an extended period and water supplies start to shrink. It doesn't arrive with a dramatic event. It begins simply when the rain stops coming. Droughts can last weeks, months, or even years. Some develop slowly across seasons, while others appear more abruptly after a dry winter or a failed monsoon cycle. Their effects depend on the landscape and the community involved, but the impacts are wide ranging: declining river levels, emptying reservoirs, drying soil, stressed ecosystems, and crop failures. In severe cases, Droughts can contribute to famine, large scale forest stress, or population displacement when water becomes too scarce to support daily life. Scientists describe droughts using several categories. Meteorological drought refers to a deficiency in rainfall. Agricultural drought is defined by reduced soil moisture that affects crops and livestock. Hydrological drought is related to low water levels in rivers, lakes, and groundwater. Socioeconomic drought occurs when water shortages begin to affect society and the economy, such as when cities impose water restrictions, farms reduce irrigation, and food prices rise as a result. Many factors can trigger or worsen drought conditions. Large scale climate patterns, such as El Nino and La Nina, can dramatically alter rainfall distribution around the world. El Nino often brings drier conditions to regions like Australia and Southeast Asia, while La Nina can reduce rainfall in the southwestern United States by shifting jet stream patterns. Persistent high pressure systems, ocean temperature changes, and long term climate variability can also contribute. Drought is closely tied to rising global temperatures. As temperatures increase, evaporation rates climb, causing water to disappear more quickly from soil, lakes, rivers, and vegetation. Even when rain finally arrives, it may not be enough to replace what has evaporated. In fact, heavy rainfall following a drought often fails to soak into hardened soil, leading to rapid runoff and sometimes flash flooding rather than genuine replenishment. Heat waves and droughts also reinforce one another. Dry soil reduces evaporation, which normally helps cool the surface. With less moisture available, the sun's energy goes directly into heating the land and air. This drives temperatures even higher, which further dries the soil. This feedback loop can trap regions in extended periods of hot, arid weather. Although both heat waves and droughts are natural parts of Earth's climate system and have occurred throughout history, their frequency and intensity have increased in many areas over recent decades. Climate scientists attribute much of this trend to global warming. A warmer atmosphere holds more energy and moisture, which increases the likelihood of extreme events, including prolonged heat and extended drought. Pilots and passengers often talk about another subtle atmospheric effect called a glory, sometimes referred to as the glory of the pilot. It appears as a series of colorful rings surrounding the shadow of an aircraft on a cloud layer below. The effect arises from sunlight interacting with tiny water droplets, causing backscattering and diffraction that form these tight, circular bands of color. Closely related are coronas, which develop when light bends around individual droplets. Unlike large halos that spread widely around the sun or moon, coronas stay close to the bright source and form small pearly rings. They're usually seen through thin layers of cloud or mist and tend to look soft and compact, almost like a delicate glow hugging the sun or moon. And then there are the sky's more dramatic beams, known as crepuscular rays, often called God rays. These occur when sunlight shines through gaps in clouds or mountains, producing radiant streaks that seem to fan across the sky. They appear most often near sunrise or sunset when the sun is low and shadows are long. The rays only seem to spread outward. This is a trick of perspective, the same way railroad tracks look like they converge in the distance. Dust moisture and other particles in the air help scatter the light, sharpening the contrast between the illuminated paths and the shadows. As daylight begins or ends, the atmosphere produces one more striking optical phenomenon, the green flash. This event happens right as the sun dips below the horizon or just before it rises. For a brief second, the top edge of the sun can appear green. The effect occurs because the atmosphere bends different wavelengths of light by different amounts. Shorter wavelengths like blue and green bend more than longer ones. Under very clear conditions, that final sliver of refracted sunlight can momentarily appear green. It's extremely fast, so noticing it requires good timing and a clear horizon. A more delicate nighttime phenomenon is the lunar rainbow or moonbow. These are rainbows formed not by sunlight, but by moonlight. Because moonlight is far dimmer than the sun, moonbows are usually faint and often appear whitish to the naked eye. They require a nearly full moon moisture in the air and the moon positioned low behind you. A long exposure photograph will reveal the soft colors that are otherwise difficult to see. All of these optical displays illustrate how constantly light and the atmosphere interact. Most of the time, the atmosphere is quietly bending, scattering and filtering light without drawing attention to itself. But when conditions line up just the right angle, just the right moisture, just the right clarity, the sky reveals patterns and colors that feel almost otherworldly. And the beauty of these events is that you don't need specialized tools to witness them. All it takes is awareness, patience, and the habit of looking up at the right moment. A rainbow after a summer shower, a halo around a winter sun, or a faint glory surrounding the shadow of an aircraft are all reminders that weather isn't only about motion and pressure, it's also about light, how it shifts, bends, and reflects through air and water. These moments turn the atmosphere into something more than a physical system. They transform it into a canvas. Weather, however, is not limited to isolated spectacles. It can be incredibly localized. You might be standing in sunlight while someone just a few miles away is watching rainfall, but it is also deeply global. Across the world, weather changes dramatically depending on latitude, terrain, ocean patterns, and altitude. From dense monsoon rains to swirling desert sandstorms, each region develops its own atmospheric character. To appreciate just how varied Earth's weather can be, let's take a look at some of the major regional patterns that shape life across the planet. And we'll start with one of the most influential, the monsoon. The term comes from the Arabic word musim, meaning season, and it describes a large-scale shift in wind patterns that brings dramatic seasonal changes in rainfall. Most people associate monsoons with heavy rainfall, but a monsoon is fundamentally a large-scale seasonal shift in wind patterns caused by temperature differences between land and ocean. Nowhere is this more influential than in South Asia, across India, Bangladesh, Nepal, and neighboring regions. During summer, land areas heat more quickly than the surrounding ocean, creating a broad zone of low pressure across the subcontinent. Moist air from the Indian Ocean flows toward this low pressure region, rises sharply as it encounters the Himalayas, and condenses into extensive bands of precipitation. The result is weeks, sometimes months of continuous rain. This seasonal influx of moisture is essential throughout the region. It supports agriculture, replenishes rivers, and restores groundwater. At the same time, it can trigger flooding, landslides, and major disruptions to transportation and daily routines. Even with its challenges, the monsoon remains vital, especially after the intense heat that precedes it. Farther east, countries such as Thailand, Vietnam, and the Philippines experience their own monsoon cycles, each with different timing and intensity. In East Asia, the monsoon shapes both climate and culture, bringing warm, humid summers and cold, dry winters that influence farming, building design, and city planning. In northern Australia, a comparable monsoon dominates the summer months from December through March, bringing heavy rainfall, widespread thunderstorms, and frequent lightning. Locally, this period is simply known as the wet. From here, the atmospheric story shifts dramatically as we look toward the world's deserts regions defined by extremes. Although often thought of as barren landscapes, deserts are shaped by dynamic weather patterns. In the Sahara, the largest hot desert on Earth, daytime temperatures routinely exceed 120 degrees, while nighttime temperatures can drop by 40 to 50 degrees. These abrupt changes occur because dry, sparse air cannot store heat, allowing the ground to radiate warmth quickly after sunset. Deserts are also known for powerful dust storms. In parts of North Africa and the Middle East, these events are called haboobs. They form when strong downdrafts from thunderstorms strike the ground and force loose sand and dust high into the air. These advancing walls of airborne sediment can extend for miles, drastically reduce visibility, and leave a fine layer of dust over everything in their path. Similar storms occur in Australia's interior, where red desert dust can travel across vast distances, and in the American Southwest during late summer when thunderstorm activity is at its peak. At high latitudes, the atmospheric environment changes again. In the Arctic and Antarctic, weather is shaped by cold temperatures, persistent winds, and extreme contrasts in light. Winters bring months of darkness and severe cold, while summers feature continuous daylight, rapid surface melting, and shifts in permafrost. The rhythm of these regions is set not only by temperature, but also by the unique interplay between ice-cover sunlight and the surrounding oceans. One of the defining characteristics of polar weather is the presence of katabatic winds, dense cold air flowing downslope from elevated ice-covered regions. In Antarctica, these winds can reach hurricane-strength speeds, pushing snow across the surface and producing whiteout conditions. Despite the extreme cold, both polar regions are classified as deserts because they receive very little precipitation. Much of the snow found there accumulated thousands of years ago and has remained frozen in place. When new snow does fall, it typically appears as fine ice crystals drifting slowly toward the surface. From the poles, the atmospheric pattern transitions sharply as we move toward the tropics. Regions near the equator, such as the Amazon basin, the Congo basin, and much of Southeast Asia, experience consistently high temperatures and frequent heavy rainfall. Convectional rainfall dominates here. Strong daytime heating causes warm, humid air to rise rapidly, producing tall cloud formations by afternoon and often a daily cycle of brief but intense thunderstorms. This reliable precipitation supports dense vegetation, layered forest canopies, and high levels of biodiversity. A short distance farther from the equator lie the savanna regions, where precipitation becomes seasonal. Extended dry periods alternate with well defined rainy seasons, shaping ecosystems dominated by grasses and scattered trees. Many large herbivores depend on the timing of these seasonal rains, and disruptions can affect entire food chains. Across the Pacific and Indian Oceans, island nations experience their own weather systems influenced by trade winds, tropical cyclones, and shifting ocean temperatures. One of the most important drivers is the El Nino Southern Oscillation, or ENSO. During an El Nino phase, warmer waters shift eastward across the Pacific, altering rainfall patterns across South America, Southeast Asia, Australia, and parts of Africa. In contrast, La Nina events bring cooler waters and often reverse these precipitation shifts. Ocean currents, such as the Gulf Stream in the Atlantic or the Kuroshio Current in the Pacific, further regulate climate by moving warm water toward higher latitudes. This oceanic heat transport explains why regions like the United Kingdom experience relatively mild winters compared with other locations at the same latitude. In mountainous regions, such as the Andes, Himalayas, or Rockies, elevation becomes a primary factor in determining weather. As air is forced upward along mountain slopes, it cools and loses moisture, producing orographic precipitation. The windward side of a mountain range often receives frequent rain or snow, while the leeward side experiences drying and descending air. This rain shadow effect is the reason the Atacama Desert, located just west of the Andes, is among the driest places on Earth. Along coastlines, the proximity to large bodies of water moderates temperatures and reduces seasonal extremes. Inland regions, by contrast, often experience greater temperature swings between summer and winter. Central Asia is a clear example where hot summers and cold winters are common. Meanwhile, coastal Norway, influenced by the Gulf Stream, maintains relatively mild winters despite its northern latitude. Microclimates add another layer of complexity. A shaded ravine might remain cool and damp while surrounding hills receive strong sunlight. Urban areas can produce their own heat islands through concrete and reflective surfaces raising local temperatures. Even vineyards, positioned on different slopes, can produce distinct growing conditions simply due to variations in sun exposure and airflow. Every region of Earth has a characteristic weather pattern shaped by latitude terrain, ocean influence, and atmospheric circulation. Yet the underlying physics remains consistent everywhere. Warm air rises, moisture condenses pressure, differences drive wind. From the driest deserts to the wettest rainforests, the same principles produce a wide range of outcomes. With this global diversity in mind, a natural question follows: how do we predict what will happen next? Weather forecasting relies on an understanding the present state of the atmosphere because conditions in one region influence those far away. A thunderstorm forming over Texas may be part of a larger pattern that affects weather on the East Coast or even across the Atlantic. To monitor the atmosphere, meteorologists use a global network of observation systems. Thousands of ground based weather stations collect data on temperature, humidity, wind speed, wind direction, atmospheric pressure, and precipitation. This information provides the baseline needed to begin forecasting. Some weather stations operate automatically, while others are manually monitored. Every few minutes, they transmit data to centralized systems, allowing meteorologists to assemble a real time picture of atmospheric conditions. Higher in the atmosphere, weather balloons, formerly known as radiosondes, are launched from locations around the world, typically twice per day. Each balloon carries instruments that record temperature, humidity pressure, and wind as it ascends, often reaching heights of around 20 miles before it bursts. These measurements are essential for determining the vertical structure of the atmosphere and assessing stability, moisture levels, and wind patterns at different altitudes. A major advancement in forecasting came with the introduction of satellites. Orbiting hundreds to thousands of miles above Earth, weather satellites continuously provide imagery and data from space. There are two primary types: geostationary satellites, which remain fixed over one location to supply constant monitoring, and polar orbiting satellites, which travel from pole to pole and gradually capture global coverage. Satellite instruments can detect cloud formations, sea surface temperatures, atmospheric moisture, storm development, snow cover, wildfire activity, and volcanic ash. Many of the cloud animations and global loops shown in weather reports originate from satellite data. Radar is another essential component of modern forecasting, particularly for short term or immediate weather monitoring. While satellites observe from above radar scans horizontally across the surface, weather radar systems emit pulses of radio waves that reflect off precipitation. By measuring the return signal's timing and intensity, radar detects the location, type, and movement of rain or snow. Doppler radar also identifies motion within more storms, making it especially valuable for spotting rotation that could indicate developing tornadoes. All of this information, billions of data points each day, feeds into numerical weather prediction models. These are complex computer simulations that apply the laws of physics to forecast how the atmosphere will evolve. The models divide the atmosphere into a three-dimensional grid where each grid cell represents a small volume of air. Within each cell, equations calculate changes in wind temperature, moisture, and pressure over time. The computations involve atmospheric dynamics, thermodynamics, radiation, cloud microphysics, and more. Modern supercomputers are required to run these models. Several major global models are used operationally, such as the Global Forecast System, GFS, in the United States, The European Centre for Medium Range Weather Forecasts model, ECMWF, and the UK Met Office model. Each model has strengths and weaknesses, and they often perform better for different regions or types of weather patterns. Even with sophisticated technology, forecasting contains uncertainty. The atmosphere is a chaotic system, meaning that very small differences in initial conditions can lead to significantly different outcomes. This characteristic is often illustrated by the butterfly effect, the idea that tiny changes can amplify over time. Because no measurement system is perfect, forecasts must account for this inherent sensitivity. To do so, meteorologists use ensemble forecasting. Rather than running a model a single time, they run it multiple times with slightly adjusted starting conditions. This produces a range of potential outcomes, allowing forecasters to assess probabilities and determine confidence levels. When the ensemble members largely agree, confidence in the forecast is high. When they diverge, forecasters know that the outcome is less certain and may provide a wider range of possibilities. When model runs begin to diverge, it indicates that the atmosphere is behaving in a way that is harder to predict. In these situations, forecasters must rely even more heavily on human expertise. Meteorologists compare multiple models, evaluate how local geography influences weather patterns, and draw on years of training to adjust what the computers suggest. A numerical model might not fully account for the way a particular valley accelerates winds or how a specific coastline tends to generate fog. Human interpretation remains an essential part of the process. Forecast accuracy has improved substantially over recent decades. A 3-day forecast today is about as accurate as a 1-day forecast was in the 1980s. 5-day forecasts are typically reliable, and even 10-day forecasts, while more general, can offer useful indications of upcoming trends. But the farther ahead you look, the more uncertainty grows. Small errors in the initial state amplify, and precise timing or location becomes harder to determine. Short-term forecasts, often called nowcasting, are particularly important for fast-changing events such as thunderstorms or tornadoes. These rely on high-resolution radar continuous observations and models that update every hour or even more frequently. This rapid information stream helps meteorologists issue watches and warnings that protect lives and property during severe weather. Probabilistic forecasting is also becoming more common. Instead of stating that it will rain, a forecast might say there is a 70% chance of rain. This approach better reflects the nature of atmospheric uncertainty. It helps people make informed choices about their day, whether deciding to bring an umbrella or planning an outdoor event. Forecasting extends far beyond personal convenience. Aviation relies on precise weather predictions to avoid turbulence and plan efficient routes. Shipping companies use forecasts to navigate storms. Farmers depend on rainfall and temperature projections for planting and irrigation. Energy providers adjust output based on expected heat or cold. Emergency management agencies prepare for hurricanes, floods, and wildfires using detailed forecasts. In recent years, machine learning and artificial intelligence have become part of the forecasting landscape. These systems analyze massive data sets, detect subtle patterns, and complement traditional physics based models. They are not replacements for established methods, but they are increasingly valuable tools that help refine predictions. Crowdsourced data has also become a significant resource. Millions of people now report weather conditions through apps and observation networks. These contributions fill in gaps between official stations, providing finer detail about what is happening at the ground level. So, when you see a simple forecast icon stating that tomorrow will be 72 drizzles with a 20% chance of showers, remember the complexity behind it. Satellites in orbit, radio sondes rising through the atmosphere, supercomputers solving countless equations, trained meteorologists analyzing patterns, and even observations from ordinary citizens. It all reflects an enormous global effort to understand the atmosphere. And while weather itself remains beyond our control, our ability to monitor, analyze, and predict it has reached a level that previous generations could barely imagine. Over the past century, and especially in recent decades, we've also begun to notice a broader trend. Weather patterns are shifting over longer timescales, not just day to day or season to season, but over years and decades. At the center of this long term change is a phenomenon we discuss frequently: climate change. To understand how climate change is influencing weather, we first need to make a clear distinction between weather and climate. Weather is the atmosphere's short term behavior, what's happening today, tomorrow, or over the next week. It includes conditions like rain, temperature, wind, and humidity. Climate, in contrast, describes long term patterns. It represents the average of weather over decades and tells us what's typical for a region, how much rain usually falls in spring, how cold winters tend to be, and how often storms develop. Climate has never been static. Over Earth's history, it has shifted through ice ages and warmer intervals due to natural processes such as changes in Earth's orbit, volcanic eruptions, and variations in solar output. What we're witnessing today, however, is different. The changes are happening rapidly, and the primary driver is human activity. Since the late 19th century, the average global temperature has risen by more than 2 degrees. For a system as large and interconnected as Earth's climate, this amount of warming is significant. The underlying mechanism is the greenhouse effect. Greenhouse gases, including carbon dioxide, methane, nitrous oxide, and water vapor, trap heat in the atmosphere. This effect is natural and necessary for life, but human activities have magnified it dramatically. Carbon dioxide is the major contributor. It is released through the burning of fossil fuels such as coal oil and natural gas. Deforestation exacerbates the problem by reducing the number of trees available to absorb CO2. As greenhouse gas levels rise, more heat is retained in the atmosphere, warming the planet. And this warming does not simply translate to higher temperatures, it reshapes weather patterns across the globe. Heat waves offer a clear example. These extended periods of extreme heat are becoming more frequent, longer, and more intense. Events that once occurred roughly once in a generation now happen every few years or even annually in some regions. Cities are especially vulnerable due to the urban heat island effect, where concrete and asphalt absorb and retain heat. Nights are warming faster than days, as well, reducing overnight cooling and increasing stress on people, crops, and livestock. Precipitation patterns are shifting too. Warmer air can hold more moisture, about 4% more for every 1 degree of increase in temperature. This means that when it rains, the rainfall is often heavier. Intense downpours are becoming more common, overwhelming storm drains, increasing flood risk, and accelerating soil erosion. But while some regions are seeing more extreme rain, others are experiencing worsening droughts. Higher temperatures dry out soils, reduce river flow, and stress ecosystems. In many areas already prone to drought, such as the southwestern United States, southern Europe, and parts of Africa, dry periods are becoming more severe and persistent. This combination, wetter wet seasons and drier dry seasons, is a signature pattern of climate change. Storm behavior is changing as well. Warmer oceans supply more energy to tropical storms, which can lead to stronger hurricanes, typhoons, and cyclones. While the overall number of storms may not have increased significantly, the proportion of high intensity storms has. More Category 4 and Category 5 storms are occurring, and they carry greater risks of wind damage and inland flooding. Recent storms like Harvey and Florence demonstrated how warmer oceans and a moisture rich atmosphere can produce extraordinary rainfall totals. Winter weather is also affected. A warmer atmosphere does not eliminate snow. In some regions, it can actually increase snowfall because the air holds more moisture. But snow seasons are shifting. They are starting later, ending earlier, and producing less reliable snowpack, which impacts water resources in regions that depend on spring melt. The jet stream is undergoing changes as well. The Arctic is warming more quickly than lower latitudes, reducing the temperature gradient that helps drive the jet stream. This weakening can cause the jet stream to slow and meander, creating large atmospheric waves. When this happens, weather systems can stall in place, leading to prolonged rain, extended heat waves, or persistent cold spells. These stalled systems have been linked to several recent extreme events, from European heat waves to prolonged flooding in the United States. There is also sea level rise, which isn't weather by itself, but significantly affects how weather impacts coastal regions. As glaciers melt and the oceans warm and expand, global sea levels have risen by roughly 8 inches since the late 1800s. Higher sea levels make storm surges and tidal flooding more damaging, pushing water farther inland and affecting more people than in the past. Climate change also influences wildfires, not directly through flames, but through the environmental conditions that allow fires to ignite and spread. Hotter temperatures, drier soils, and earlier snowmelt lengthen fire seasons and increase the availability of dry vegetation. Lightning strikes, which ignite many naturally occurring fires, may also become more common as convective storms grow more intense. Once a fire begins, strong winds and dry fuels help it spread quickly. The result is more frequent, more severe and more destructive wildfires across regions such as California, Australia, and Siberia. This doesn't mean every weather event is caused by climate change. Weather will always vary. Cold spells will still happen. Rainy seasons will still occur. Calm years will still appear between more active ones. But scientists can now analyze how climate change increases the likelihood or intensity of particular events. This field, called attribution science, helps us understand how a warming world influences the atmosphere's behavior and shifts the baseline conditions behind everyday weather. The next question is, what can be done? Not all change is inevitable. Some warming is already locked in due to past emissions, but future outcomes depend on decisions we make now. Reducing greenhouse gas emissions, transitioning to renewable energy, improving energy efficiency, protecting forests, and changing land use practices all play a role in slowing the pace of climate change. Adaptation is equally important. Communities are redesigning infrastructure to handle heavier rainfall, planting trees, to reduce urban heat, updating building codes, to withstand stronger storms, and rethinking coastal planning as sea levels rise. Farmers are adopting drought resistant crops. Cities are mapping flood prone areas and building seawalls. Individuals are learning strategies to stay safe during extreme heat, conserve water, and reduce their carbon footprint. Small actions matter when multiplied across millions of people. Walking instead of driving, reducing unnecessary energy use, supporting environmental policies, and making informed choices all contribute to meaningful change. Each decision adds up the same way individual raindrops accumulate into a larger storm. Weather is still weather variable dynamic and sometimes surprising, but the conditions it develops within are shifting. The boundaries have changed. The patterns are evolving. We are both observers and participants as this transition unfolds. So the next time a summer heat wave lingers longer than expected, or a storm drops more rain than you're used to seeing, remember that you're experiencing part of a broader story. A planet adjusting a system in motion, and a future still shaped by choices made today. And so we've drifted through winds and rain, moved with clouds, and stood in the quiet stillness of falling snow. We've explored lightning-filled skies, watched deserts shimmer under heat, and followed the forces that guide weather from one region of the globe to another. From gentle fog to powerful hurricanes, from the behavior of sunlight to the movement of air, we've uncovered pieces of how this intricate, ever-changing system operates. Weather is more than background noise. It is a continuous exchange between the earth, the oceans, and the atmosphere, a process of temperature, water, and motion interacting across scales. It shapes landscapes, influences daily life, and delivers both opportunities and challenges. And despite all our tools, satellites, and models, the atmosphere still manages to surprise us. Even as you settle in tonight, wherever you happen to be, the air above you remains in motion. Winds continue sliding over ridges and rooftops. Moisture gathers quietly on leaves. And somewhere far across the globe, a tiny crystal of ice is just beginning to take shape. It's a reminder that the sky never fully rests. It simply shifts from one state to another carrying on its continuous cycle around the clock. Before we finish, I'll ask once more, where are you listening from tonight? And what time is it for you right now? Whether it's late at night, early in the morning, or a calm moment in the middle of the day. I'm grateful you chose to spend this time here, unwinding and exploring the science of weather with me. If this session brought you any calm curiosity or simply helped you drift a little closer to sleep, feel free to leave a like or subscribe to The Sleepy Scientist. It helps others discover these quiet explorations and supports the work that goes into creating them. For now, take a long, comfortable breath. Let your thoughts settle the way air settles after a passing front. And may your rest be steady and peaceful, like the clear, quiet atmosphere that follows a gentle rainfall.